Okay, welcome back, guys. So, I was able to fix the issue with the pot lights. I don't actually know what the issue was, so you'll just have to deal with it on the last video. I mean, I could reshoot it, but it was like 30 minutes. I'm not doing it. All right, so I think you can cope. You're all adults. I also got a new marker, so hopefully that helps as well. So what were we doing before the break? Well, we're trying to analyze this MG1Q, and we want to get the system performance, the system metrics of the MG1Q. And when I say that, I mean things like the expected number of jobs in the system, the expected response time, etc. But those are the two main ones that we're really after. And what we were doing is building up a recursion, not necessarily for the number of jobs in the system, but we're looking at the number of jobs in the system when a job departs. As it turns out, those things are going to be equal, but that's the way we're going to view it. We're now looking at the number of jobs in the system as a job leaves the system. Okay, and we're able to build this recursion here. And before the break, I introduced you to this Heaviside step function, which you've probably, I hope you've seen in your math courses before. It's nothing fancy. It's just a function where it's going to evaluate to 0 if its input parameter is 0, and it's going to evaluate to 1 otherwise. Okay, so it's nothing crazy. It's just, a mathematical way to write, things conveniently. And here's an example. So I want to write an expression for this variable here, n subscript n plus 1. So the number of jobs seen in the system if it's the nth plus 1th job leaves the system. I want to write that in terms of a single line expression. So I don't want cases anymore using the Heaviside step function. How am I going to do that? Well, you just look at it, you make a couple observations. Well, here, this is the case where n subscript n, number of jobs seen in the system by the nth job, this is when it equals 0. Well, if it equals 0, I can just write it as a tag on here. And now I see, okay, well, in both cases, no matter what, n plus 1 equals nn plus a n plus 1. Okay. So n plus 1 equals nn. It's nice. It's nice to have a new marker. Plus a n plus 1. Now we have to be a little bit careful. So in this case, I don't want to minus anything off. In this case, I want to minus 1 off. Well, how am I going to do that? Well, of course, I have this Heaviside step function. So I'm just going to minus the Heaviside step function at nn. I can give it a random variable. It's no problem. This just becomes itself a random variable. Okay. So before I take expectations and, let n go to infinity and do all this stuff to get these steady state values, let's maybe look at some individual terms here. Let's first consider the expectation of this. Well, you can think this is going to equal 0 when there's 0 jobs in the system, and it's going to equal 1 when there's more than 0 jobs in the system. So that's actually like an indicator variable for the probability or the fact that there's jobs in the system. If there's more than one job in the system or if the system's empty. But you can review your stats, and if that's an indicator variable, then the expectation is going to equal the probability that nn is greater than 0. So this equals the probability that the system's busy, that there's more than one job in the system. Well, before, with like MM1 systems, a lot of other systems, that was just the utilization. And in fact, nothing's going to change. It's also going to be the utilization for the MG1Q. What's the utilization? Just lambda over mu. So that's one thing that remains constant between our analysis from MM1 to MG1. The probability the system's busy is still going to equal the system's utilization. So this equals rho, which equals lambda over mu. Okay, well that's good. That means we know the expectation of that value. That's going to help, moving forward, hopefully. What about the expected value of an? So what's the expected number of jobs to arrive during the nth job's processing time? Well, I don't really know anything about, if it's the 10th job's processing time, 11th job, and really its processing time, its service time is completely independent from when it, if it's, 10th job, 100th job, first job, etc. So it's not going to be dependent on that, but we'll leave the subscript there for now. Well, what does this equal? Well, let me phrase it in a different way. What's the expected number of jobs to arrive during a time interval t? During an interval, I guess I should leave a little bit more space there. Interval t. So if I have some interval t, and jobs arrive following the Poisson process with rate lambda, how many jobs am I expecting to see? Well, you can imagine, think of it this way. If jobs arrive 1 per second, and the time interval is 1 second, how many jobs will I expect to see? 1. Very good. If I had jobs arriving, 1 per second, and the time interval was 10 seconds, it's 10. If jobs arrive 2 per second, and it's for 5 seconds, it's 10, right? Doing some quick math here. Well, this is going to equal lambda t. Okay. Well, then what's this? Well, this is asking what's the expected number of jobs that arrive during, a job service time. Well, that's now a random interval, but we can just take the expectation of that interval and we'll get the expectation of the number of jobs that arrive. So this is going to equal lambda times the expected service time. The expected service time, remember, is 1 over mu. The service rate is mu. The expected service time is 1 over mu. But that, of course, also equals rho. Okay, well, that means I can get the expected value of an. That's good news. That's good news. Okay, well, if I can get those two values, maybe that's going to allow me to analyze this further and hopefully get the steady state value for the expected number of jobs in the system. So I'm going to let n approach infinity. Why am I letting n approach infinity? I'm interested in steady state value. So we let n approach infinity. Essentially what happens here, and you've probably seen this in your recursions and your other mathematics course, is you get infinity, 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 and you end up dropping the subscripts. But this implies n equals n plus a minus mu of n. Okay, so now we switch to steady state values by letting n approach infinity. And we have to be a little bit careful here because this is really the steady state value of jobs seeing what a job that's departing sees in the system, as time approaches infinity. But as we discussed last time, that actually, in fact, is equivalent to the true steady state values of the system. So I'm playing it a little loose with my notation, but everything's fine. If you review, it all works out. N right here is going to denote the number of jobs in the system. And we end up with this formula. Okay, well, I want the expected number of jobs in the system. So I'm going to take the expectation of both sides and see what I get. Okay, well, I know expectation is a linear transformation. It's a linear function. That means I can just take the expectation of each of these variables, random variables, and it seems like we're in business. Okay, hold on. What's going on? Well, these cancel out. And what's this equation telling me exactly? Oh. So what I was trying to solve for actually ended up canceling out. And the only thing that this equation told me was the expected value of u at n equals the expected value of a. Well, that's something, right? Or is it? Is that any new information? Wait, hold on. I already knew that. I knew that the expected value of an equals rho no matter what the n is, and I knew the expected value of the Heaviside function at nn, no matter what lowercase n is, also equals rho. What have I done here? Did I screw something up? So it seems like this equation actually doesn't give us any new information. Maybe. Is there anything we can do? It's like there's no information in this equation that we didn't already know. Now this next step I'm going to show you is going to rub a lot of you the wrong way, because like the first time you see it, you're like, wow, it kind of makes you rethink the way you think about mathematics, at least the way you think about random variables. And let's consider this trick. Okay, so this equation doesn't tell us anything really, but what if I square both sides? Does that reveal any new information? If I square both sides? Let's find out. Okay, so I get n squared equals n plus a plus u of n squared. Now, I might make a mistake here, but follow along. You tell me if I've made a mistake. So we get n, you know what? And I'm being honest when I say I could make a mistake. So let me just write it all out so I can see all these terms. See, I do my best to do these lectures without looking at my notes, but it can get tricky sometimes. So I'm going to get n squared plus an or na plus n un plus, and I mean, you can always fast forward if you don't want to see me struggle with this, but I know you guys enjoy seeing me struggle, so I'm here for your entertainment. Okay, plus another an, so we can probably collect those terms afterwards, plus a squared plus aun almost there, plus nun plus aun Okay, double check my work, make sure I haven't made any mistakes. I should get, what, 9 terms? 1, 2, 3, 4, 5, 6, 7, 8, 9. Good. Collect all the like terms, should end up with 6 terms after. So n squared plus, do all the squares, a squared plus u squared at n. plus 2 NA plus 2 N UN plus 2 A UN. Okay, I think I've done that correctly. Again, double check my work. Now what happens if we take the expectation of both sides? So I'm going to have the expected value of this, and again we'll just use the linearity of the expectation, plus the expected value of this, plus the expected value of this, plus the expected value of this, so on and so forth. But let's see if we can make some simplifications that might help us out. Okay. Well, I know the expected value of UN equals rho, and I know the expected value of A equals rho. What about this term? I'm not taking the expectation yet, but the Heaviside function squared. What does this equal? So I can rewrite this as follows. U of n times U of n, just so we're not confused by what that where that square is. Okay. Well, the Heaviside step function can equal one of two things, 0 or 1. If this equals 0, this entire thing equals 0. If it equals 1, the entire thing equals 1. Well, this equals this. Huh, okay. Interesting. Well, are there some other terms in here that could be an issue? Let's take a look at this one. And see, whenever we take expectations, it can get tricky if these random variables, if we have a product of random variables and they're dependent on each other. If they're independent from each other, then the expectations are just, separate out. But if they're dependent on each other, like this, clearly this term is dependent on n. So we can't just say the expected value of n times the expected value of n times u at n does not equal the expected value of n times the expected value of u at n. So is there anything else we can note? Does this equal something? Well, when this equals 0, what does this equal? When n equals 0, this term equals 0. When n doesn't equal 0, this equals n. So when n equals 0, this equals 0, and when n doesn't equal 0, this equals n. That means this equals n. Oh. Okay. Now we're getting somewhere. Okay, so we've kind of worked with this one here. We've addressed this one. We still have a couple others to address. And let's think about this. The expected value of n, A, well, what's A? A is the expected number of arrivals for any service time. That's not actually dependent on n. You think, well, you just give me mu, and that's going to be basically lambda over 1 over mu. It's not like if there's 100 jobs in the system, that doesn't mean that, the next service time is going to have, a longer service time or a shorter service time or anything like that. So this ends up equaling this, but we know what this is. So this equals rho, the expected number of jobs in the system. And we make a similar observation down here. The expected value of A times the Heaviside function, Heaviside step function. This is also going to equal this from the independence of these two random variables, but we know what that equals. That's rho squared. Okay, and I guess I didn't finish this off, but of course this implies that the expected value of n u of n, that equals the expected value of n, and this implies the expected value of u squared at n equals rho. So I'm kind of addressing this term by term and seeing if I can make some simplifications or see if I just know it. Okay. So I know this one, this one, this one, and this one. I'm left with two things. I'm left with the expected value of n squared and the expected value of a squared. Well, I'm trying to solve the expected value of n. And if I don't know what the expected value of n is, I'm going to have a real hard time coming up with the expected value of n squared. But I don't have to worry about solving the expected value of n squared. Why not? Because they cancel out. Oh. So now all I have to worry about is the expected value of a squared. So the second moment of a. So that one's, we can't make any clever or cute observations about that, but you can just brute force this sucker with statistics, and let me just double check my notes on this one. What does that equal again? Yeah. Rho plus rho squared plus lambda squared times the variance of the service time. So here, this is the variance of the service time distribution. Okay, so right here, this equals the variance of s. Okay, so sigma lowercase s is like the standard deviation of the service time distribution, and of course when we square the standard deviation we get the variance. Let me just make sure I copied that correctly. Okay, very good, very good. Well, what do we get? Uh-oh, I've spotted an error. This was minus what, and I squared it and I didn't bring the minus over? Oh my god. Are you kidding me? Why didn't you tell me, guys? Oh boy. So I'm way too far in to just pretend like I didn't make that error and then reshoot it. So let's plus I think I fixed it. Whew! That was close. I almost lost marks. Okay. So what does that mean? Well, we just kind of rearrange everything, and we get that the expectation of, and I'll just bring all the negative ones over. So 2 times the expectation of n u of n plus 2 times the expectation of a u of n equals unless I've made a mistake here. Oh no, my reference. Okay, we can recover. Okay, so what do we get? Well, basically, from here, it's just all algebra. So we're going to look at each term, just sub in what we've noticed already. And we say, okay, well, this is 2 times the expectation, rho times the expectation of n plus, follow it through. This is also rho times the expectation of n. There's probably some simplifications you can do there. Equals 2 times rho squared. Oh, whoops, I forgot my, oh, no, I took the wrong term there. So this is rho squared, right up here. So plus rho squared. So I guess I could, yeah, I'll write it like that for now. Okay, so this equals, sub this sucker in, rho plus rho squared plus rho. And you start to see we probably cancel some rows out and stuff like that. Plus 2 times rho what is going on? What is going on? Aha. Made a mistake here. I said that that was rho times the expected value of n. But we come back over to, where was it? Here. This is just the expected value of n. Okay, I think that's correct. Double check it, see if you can follow the derivation here. But basically, I was worried there for a second, because if it was rho here, then these cancel out again. We lose our term with, you know, the expected value of n, which is what we want to solve. However, that's because I forgot that little error there. The final expression we get looks something like this. After you do all your simplifications and calculations. Geez, man, this video is just riddled with errors. So, I was in a meeting with a bunch of the professors, and we're like discussing, you know, how we're doing these lectures. And I was like, I'm just posting lectures online. And the one lecturer was, yeah, but the one professor was like, but what if you make a mistake? I was like, I don't care, right? I'm secure with my intelligence that I know that these mistakes aren't a big deal, right? Plus, it humanizes me. I mean, shows you we all make mistakes, right? So, just bear with me on this one. Like I said, it's just a consequence, well, partially a consequence of me trying to do all this stuff without looking at notes. But that's half the fun. After all the algebra, we should get something like this. So, as an exercise for you, take this, simplify it to this. If it doesn't simplify it to that, work backwards and find where I made the mistake or mistakes, okay? But all of this stuff should make sense, and then, you know, you can rewind the video. I don't have the luxury of rewinding the video to seeing this expression here, but it does all work out. Just check the algebra, the simplifications. What you should get is something like this, and what this is called and if you thought I made some mistakes before, just listen to the pronunciation of this once I get it written out. The Polychuk-Kinchin formula, and I apologize to all the Russians and Eastern Europeans out there, but this is the expected number of jobs in an MG1Q. How do I get the expected response time? Just apply Little's law and it'll all work out. So of course we know that the expected response time, the expected number of jobs in the system equals lambda times the expected response time. Okay, so I think we can end there, and you know, not the full lecture, just this section of the lecture, just this part of the lecture, and then we'll do a couple problems where we apply this formula. Okay, thanks for your attention and your patience. I'll catch you in the next lecture.